All right, so last class, we looked at this idea of inverse variation, where it's just y equals k over x. Now, as we start looking at this, one of the easy applications, we can do it with just x and y. The main point of this is once we get an x and a y and we're told that it's inverse variation, let's just find the value of k. That's all that we're after. Now, for today's problem, we're going to use a little bit of editing magic. I would encourage that you write this with less words than I'm about to, just so you know, because it is a word problem. But we're told that the frequency, and we'll just call this f, the frequency f of a string of length s. So we have the frequency of a string, which, for those of you that don't recall from physical science, if you pluck a string, it's going to oscillate back and forth. It's going to do this sort of thing. And how many times it does that per second is known as its frequency. So the frequency of a string of length s varies inversely, very inversely. Now, I worded that oddly, but frequency varies inversely as length. That's what we're stating here. Okay, so let's say that we have a ukulele, and I'm going to shorthand that with uke. A uke has a string length, and I'm just going to call that S, since that's we've already defined it as, of 26 inches. So it's like a big ukulele, 26 inches, and a frequency of 329, I'm going to say F equals, thank you, Mrs. Holloway, 329.63 hertz. So we have this inverse variation happening where we tell that there's an inverse relationship between the frequency, the pitch of that string, and the length of it. What I want us to do is if we take the same string and make it half as long, I want to know what changes with the frequency. So we'll say find f, find the frequency f, if the string length s is 13 inches instead. Now, for this, we should expect a higher frequency. For the shorter string, like Sunny demonstrated well just a minute ago, there should be a much higher pitch. And what we should find is a frequency bigger than this. And I think that we will. But if we want to be able to write a model out for this, we need to automatically be able to just jump right in and say, well, here's the model that we can use. Right off the bat, this varies inversely statement right here is what we really need. If I wanted to write this model, I can say that f is equal to what? If we want to use inverse variation like we did on the previous example. K over s. So frequency f varies inversely with some constant k to the length of the string. Now, what I want you guys to do is using the information that we have, I want you guys to find me a value for k. You are going to need a calculator. There's a bunch of them up in here, but I'm going to give you guys a minute. Find me the value of k from this example, and we'll meet back up in about 60 seconds. Remember, there's a whole bunch of them right up here, too. Cool. Okay, as we're coming together, you guys have calculators in front of you. We're going to plug into this f. So my frequency f is that lovely 329.63. So 329.63 is equal to k over, what's the length of that string? 26. Now, if I want to solve this for k, I just multiply both sides by what? By 26. So I'm just going to show doing that. I don't have a calculator handy. We'll do 26 here, and the 26 here. And what do we wind up with for k? 8563.36. Awesome. Now, what we see here is just some constant. It won't change. It's always going to be the same for this size string. It's just changing how big it is. Once we have this, are we done with the problem? No, because we found k. That's a pretty good step in the right direction. Did you guys get the same number? let's do it real quick. I think we should have gotten 8570.38. I think. Can somebody verify 8570? Okay. Kennedy, if you check your calculator, my guess is you have a 6.6 instead, or a 3.3. So I'm going to fix that value. Okay, 8570 point, what was it? 8570.38. Okay. I'm going to come look at your calculator because that's strange. Eli, what does it say on mine when I did it? What did I get for K? This thing? Okay. So I'll come check yours out, Kennedy, here in just a second. Now, we're almost done. We now know that we have a value of K that fits right in here. If I want to find the frequency F of any string now, of any length, we're just going to use this lovely number, 8570.38, and we're going to divide it by whatever S is. When we divide this by the string length 13, since it's half the length, what do we get for the frequency? So I'm going to say when S equals 13 instead, F equals, and what do we get? 8570.38 divided by 13. 659.26? Is that a higher frequency than we started with initially? For sure. In fact, it's twice as high. If we cut the string in half, the frequency will be twice as high, and this is a pretty fundamental part of how instruments work. Do these problems seem wildly difficult? No. Even in the word problem situation, as long as you can pick out this varies inversely situation, we know it's going to be this model, and it's going to work nice and easily to work out. Cool, cool? What questions do you have about this one before we move on? Okay, so looking at this, I'm going to have to steal my notes back from you, Eli, because I don't remember where else we go. From here, we start to talk about this idea of some new types of functions. Now, remember, the name of this chapter is Q functions, is how we wrote it. Which, what does that Q represent? Rational. And what's a ratio? Fractions. So, as we're looking at this, we actually get some calculus on accident here, but we'll get that out of the way. Our next topic, and we're nearly done with the section here, which is pretty sweet. All right, I need to turn down my phone. I'm terribly sorry about that, guys. I bought a continuing on. Our second topic, and it will go pretty quick in here. We're still in 4.1 inverse variation stuff. We are going to define for ourselves the reciprocal function. And I'm going to ask one random person. I'm going to go lock the door real quick out front. But in like 30 seconds, I'm going to come back, and I want one person I'm going to call randomly. I want you to tell me what reciprocals are, because we use them all the time. It is exactly that nice thing that undoes or is the flipped reciprocal of our nicest function that we have, our identity function. So we'll define this super quick and easy. We'll say that this is defined, the reciprocal function, as f of x equals simply 1 over x. That's it. Now, what we see happening with this is a few different things. We get something that we haven't had to deal with this year. If we pick a number kind of close to 0, like that's pretty vague right now, but on your calculators, since most of you guys have them, let's pick numbers pretty close to 0. We'll start at 1. If I did 1 over 1, what does it give me? What if you did 1 over 1/2? Are you sure it's 0.5? Ask your calculator. 1 divided by 1/2. We're going to get closer and closer and closer to 0. 1 divided by 0.5, which is 1/2, right? I think it gives me 2, doesn't it? What about 1 divided by 1/10? Or 1 divided by 0.1, if you will. It's not 3. 10. As we get closer and closer to 0, whatever number it is, we see that this function gets bigger and bigger and bigger and bigger forever. So we get a new phrase in here. We're going to make a pretty mathy statement here that is an important idea that you're going to see moving forward in like every math class that we go toward. So we're going to say as x And I'm going to use this arrow, which henceforth I won't write it, but this arrow means approaches. As x approaches 0, f of x approaches, and I want to look at the graph of this really quickly because we get a sweet new type of idea that we've never had to deal with or gotten to deal with before. So as x approaches 0, what does f of x do? If I pick 1/2, it goes to 2. If I pick 1/3, it goes to 3. If I pick 1/10, it goes all the way to 10. The closer I get to 0, what happens to the y values, the f of x that it spits out at me? They get bigger and bigger and bigger, right? Just like we saw with the inverse variation. As x gets smaller, y gets bigger. Now, if we look at the actual graph of this, y, and I'll even use f of x, here's all of a sudden this new type of graph that we get to deal with. As I get closer and closer and closer, does it just blow up toward infinity? Now, as I do it from the negative side, as x gets bigger and bigger and bigger, which it feels weird because bigger in this context just means closer to 0, does the y value get smaller and smaller and smaller or more negative? So we see the exact same thing that happened with the inverse variation. We see as x approaches 0, f of x approaches, and I'm going to sneak this in here, plus or minus infinity. And it depends on the side that we're coming from. If I come from the negative side, we'll go down to negative infinity. If I come from the positive side, it blows all the way up. Okay, this idea, have you guys seen the graphs that look anything like what I just showed? Any time that we get this thing. Now, if we wanted to look at this, and I can shift this around a little bit, do we agree that it kind of looks like it's getting closer and closer to this blue line? Like, it might even look like it joins it, but if we zoom way in, does it actually touch it? It doesn't quite touch it. And if I go up a little further where it looks like it does touch it, like all the way up here, if I zoom in, do you think we're going to see them touch, or are they just going to be really close? Really close. Really close. Now, how close will they get? Like, am I ever going to touch it? No. So what we see here is a new idea. I'm not sure if you guys have ever seen this word, but when I was student teaching, and this is just a random personal story, my student teacher that I worked with did not like me. She was not a fan of me and me not a fan of her, which that's whatever. It's a professional relationship. But she said this word in a way that has bugged me year after year ever since. So we're going to sneak in a definition here, and we're going to define this word. Okay. Now, the word that we see here, asymptote. How would you say that, Fred? Asymptote? Okay. My student teacher, for whatever reason, asymptote. She added an extra sound in there, and it still annoys me to this day. Asymptote. That's what we have just seen evidence of for the first time, an asymptote. Now, for our purposes, we're going to see throughout this chapter, we get a few different flavors of these asymptotes. They can be vertical, like the one that we just saw. There's going to be horizontals, and whether we see it this year or next, there's also some diagonal or slanted ones. But we're going to say that by definition, an asymptote, which will show up with these functions, is simply going to be a line on a graph, that a function gets arbitrarily close to. So, as we look at these, like I mentioned a moment ago, there are a few different flavors of these. The vertical asymptotes are super easy to identify from a graph. In fact, the horizontals are going to be generally pretty easy to identify as well, but we're going to sneak in a couple more comments. We get really, really close to that line without ever actually touching it. If I go back to this lovely function here, bless you, I think it's probably pretty clear that there's a vertical line that I never touch. It's that blue line that I just made disappear, right here. Now that happens when x is what value? And it just so happens that if I were to plug in 0 for x, it would try to make me do what? What am I trying to divide by in that situation? 0. So it turns out there's an easy way to recognize where these asymptotes live from a function without ever having to graph it. We're going to sneak a couple more in here. We'll say vertical asymptotes. And for the record, you will never see me write this again. Vertical asymptote will just be VA. We get a vertical asymptote, and they're easy to find. It happens when I try to divide by 0, because the closer I get, the bigger that the overall number comes. We'll just say vertical asymptotes, easy to define, which values, or the x values rather, the x values that make me divide by 0. We're not allowed to divide by 0 because we blow up to infinity in those situations. It is unbounded, everything goes crazy. Vertical asymptote, the x values that make me divide by 0. Now, there are horizontal asymptotes as well. We're not going to get as into them right here, but we'll be able to see them on the graphs. As we look at this graph here, is there a horizontal line that I get really close to but I never quite touch? What do you think that horizontal line is? So you say x, I think I know what you mean. Can you be more specific with that, Michael? Because if you just say x equals is going to give me a vertical line. X equals 0 is that vertical line that we didn't touch. But I assume that we can all see that this horizontal line right here, right? There it is. Y equals 0. This green line, if I look at it, do I ever touch it? No, and I get really close to touching it, but I will never quite touch it. Even at a trillion, 1 over a trillion is almost 0, but it's not quite 0, right? And it turns out there's some easy ways to find those as well, but it's not going to be as much of our focus. So we have one last example that we're going to look at. And I'm just going to throw a graph up on the board. We're not graphing these things by hand right now. We will here in the coming sections and see that they're pretty straightforward once we can find the asymptotes. But for the following, you can sketch it if you want to, but all I need from you is, I'll put the graph up here, I want us to find, for the following graph, the vertical asymptote, or asymptotes if there's more than one. And then I didn't define this one, but what do you think HA represents? The horizontal asymptote, the domain, and the range. And I'm just going to give you the graph. And I'll even give you the equation if you want real quick. We'll just look at it. The equation that we're going to graph and that I'm going to graph is given by f of x equals 1 divided by x minus 1 plus 2. Now, just to demonstrate real quickly that these things are oftentimes easier than it might feel initially, you probably don't have a great feel for what this graph looks like. That would be my guess. Do you think it's been moved left 1 or right 1, based on all the HK stuff that we've discussed earlier in the year? Right 1, and what do you think the plus 2 is going to do to it? Up 2. Now, if I asked right now, before we did anything else, is there a value of x that makes me divide by 0? Are there any values of x that would make that happen? At positive 1, right? Like if I plug in a positive 1 here, it would make me do 1 over 0. So that should be our indication that we do have an asymptote there. But I want to verify. We'll get rid of these guys. We'll go back home and do that. So we have 1 over x plus 1 plus 2. X minus 1, thank you, plus 2. From this graph, and I'll make it a little bit bigger so we can all see it. From this graph that we have on the board, I want you guys to identify for me the vertical asymptote, if there is one, the horizontal asymptote, if there is one, the domain and the range of this function. I'm going to give you guys like 60 seconds, chat it out with one another. We'll debrief afterward, and we should have a ton of time to work on stuff. Cool. I'll pause it here. Talk it out. We just found the vertical asymptote was at which x value? X equals 1, right off the bat. Now, I don't really care the way that we write these out, but I'm going to make sure that they match. Where's the horizontal asymptote? At the y value. But why didn't I ever touch here? At 2. So we've answered the asymptote questions from the graph. The vertical one we can do really straightforward without this, but we can, there's tricks around this as well. If this is the only x value that I never touch, my only asymptote, it means every other x is fair game, right? So how do I write that domain? Every x except this one. Not really rhetorical, although it might have seemed that way. I'm going to have you guys help me. If we want to talk about the domain of this thing, do we want set builder? Do we want interval? Interval, okay, I'm going to go set builder first, just to make sure we hit both of them then. I'm fine with that. What x did we say we don't use? X such that x can't be what? So it could be greater than 1 or less than 1. Do you guys agree that that's just a fancy way of saying don't let x equal 1? Boom, let's just say that. X such that x is not 1. And we have it. Every other x value is fine. Now, if you want it in interval notation, I'm fine with that. How far to the left does our graph start? Oops, I got on the wrong graph there. Infinitely far left until where do we get weird? At 1, right? Not 0, because we've been shifted. So we'll just say, okay, interval, that's fine, negative infinity, up to 1. And then we union that, we pick back up on the other side of 1 and go how far to the right? Infinity. Yeah, we're never going to stop going. We just have to jump over that x equals 1 value. The one place where it makes me divide by 0. For the range, very similar idea. If we have our vertical asymptote, we've shown all the places that my x's don't get used. The horizontal asymptote instead, in this context, and there's a bit of strangeness that'll happen with this later, but every y value except for what got used just now. Everything except for 2. And if we look at the graph, I can see that that is indeed true. Every value smaller than 2 is going to get hit at some point along this curve, and every value bigger than 2 will get hit. Is there an easy way that we can say the range then? It's the set of all y's such that what is true about y? It is never equal to 2. Now, we will see there are situations, vertical asymptotes, we will never, ever, ever, ever cross. Horizontal asymptotes, we may cross from time to time. They're the weird ones that only deal with end behavior, but we'll see that in our next section. We can make these as gross or as nice as needed, and we're just going to look at one more. You don't even have to write it down. I just want to see if we can think it out. If I give us this awful guy here, and I'm going to give it into our nice factored form. Let's say f of x is going to be 3 over x plus 2 and x minus 1. It's just this. Are there any values of x that I could plug in that you think would make me divide by 0 here? So you say 4, but if I plug in a 4, we get 6 times 3 in the denominator. Any values of x that make it 0 downstairs? 1 would make this one 0, right? And then something times 0. So x equals 1 is one of them. Is there another? At negative 2. So if I graph this, I should expect to see 2 vertical asymptotes. One is going to be at 1, and one is going to be at negative 2. Let's see if that's true. I already forgot what it was. 3 over x minus 1 and x plus 2. I think it's backward. But if we look at it, are there 2 vertical lines that this red graph will never touch? Yeah, and they're easy to pick out there. The graphs get kind of weird, and that's okay. But looking at it, if we can decide that dividing by 0 is not okay, we're always going to be able to find our asymptotes every time. Okay, we get like 20 minutes. This stuff, just gut feeling, feels okay, feels bad. Where would you put it? Okay, so we're kind of all over the place. That's good. 20 minutes of work time, which means I'm going to be walking around to do what? Well, that's one part of it, but my hope is that as, young adults who are here to do work, you're going to be working whether I'm walking around or not. But I do want to be able to answer questions if you have them. So, what we'll do now is we get time for the assignment, and let's bounce over that. See, today's a 12. Lesson 4.1.2, I suppose, inverse variation. And you guys get a little bit of assignment. So here we go. Tonight, I want you guys to work through homework 4.1, which you will find waiting for you on page 187. And I want you to work through 9 through 23 odd. Okay. we have almost 20 minutes. You should be able to get the vast majority of these problems done. I will be coming around to make sure I can answer questions if there's places where you're not quite sure about things. Let's stay on task and not make me regret this. Cool. I will keep that up. I'll end the video here real quick though.